Hello, in this lecture we are going to discuss about very important concept, the concept of Vapour pressure, concept of Vapour pressure, second important questions related to Vapour pressure, important questions related to Vapour pressure and all previous year question asked in All India, Delhi, foreign exam, all the types of PYQ will covered in this lecture. Write down the heading Vapour pressure. Vapour pressure or a pressure exerted by vapor is called vapor pressure. We will discuss the vapor pressure in the pure solvent or in a solution. Number one, vapor pressure, pressure of pure liquids. Second, second, vapor pressure of liquid solution. Okay, vapor pressure of the pure liquid. Suppose suppose a vessel suppose a closed vessel containing a volatile liquid containing a volatile liquid suppose a closed vessel containing a volatile liquid is called liquid. Volatile liquids, volatile substance are those substance which evaporate and forms a vapor, evaporates and form vapor is called volatile. Okay, so what will happen in this container? The vapor start forming, the liquid evaporate, liquid would evaporate, the vapor start forming and get accumulated in this container like this. Vapor means liquid convert into the vapor. This phenomena is called vaporization. Liquid convert into the vapor. That's why the level of the liquids decreases and the because the liquid converts into the vapor. At the same times the vapor strike same times the vapor strike the surface of the liquid and get condensed. This is called a pressure exerted by the vapor. When the vapor convert into the liquid, this phenomenon is called condensation. Both condensation and vaporization occur simultaneously. Then, at the stage when rate of vaporization is equal to rate of condensation. This stage is called equilibrium stage. This stage is called a equilibrium stage. This equilibrium stage when the rate of formation of the vapor is equal to rate of formation of vapor into the liquid when the liquid when the vapors strike above the surface of liquid and get condensed. Now, from all our discussion, now we can conclude the definition of vapor pressure. To define the vapor pressure, vapor pressure is a pressure can be defined as vapor pressure can be defined as the pressure exerted by vapor above the surface of liquid at equilibrium is called vapor pressure. Okay. Next point, we will see how the vapor pressure affected. So the factor affecting the vapor pressure. Next point is factors affecting vapor pressure. Factor affecting the vapor pressure. Factor A is the nature of liquid itself. Nature of the liquid itself. Suppose container having a water, container A having a water, and another container B having a alcohol. Container A have water and here is have alcohol. Which one have a high vapor pressure? The vapor pressure of the alcohol is high than the vapor pressure of the water. But why? This is due to the intermolecular force between the molecules of water is stronger than the intermolecular force between the molecules of alcohol. Intermolecular force, attractive force between the water molecule. This is intermolecular attractive force. Intermolecular attractive force between the molecules of water is stronger. Vapor pressure is low, or intermolecular force between the molecules of alcohol. In short, the intermolecular IMF, intermolecular attractive force between the molecules of alcohol is weaker, constitute vapor pressure high. The intermolecular force and vapor pressure is inversely proportional. So here we can conclude it with our discussion. Vapor pressure is inversely proportional to IMF, the intermolecular force between the molecules. Okay. Now we can Right here, you can write here vapor pressure, in short BP, is inversely proportional to intermolecular attractive force IMF. Intermolecular attractive force is strong or high, vapor pressure is low. This keep in the mind. Okay, let's delete all this what we have learned. Okay, we have to only keep in the mind this vapor pressure inversely proportional to intermolecular force between the molecules. Okay, next next point is temperature. How vapor pressure of this of the liquid depends on the temperature. Suppose a liquid water at temperature 50 degrees centigrade, another container having a water at 80 degrees centigrade, vapor pressure, which container have high vapor pressure, of course the container which have a high temperature, vapor pressure of this container is high. But why? This is due to at high temperature molecule possess greater kinetic energy. Okay, the temperature is directly proportional to the kinetic energy. Temperature increase, kinetic energy increase. As we know, the kinetic energy of the molecule increase, the tendency of the molecule to escape from the surface into the vapor is increased. So from our discussion, we can conclude that the vapor pressure is directly proportional to temperature. So vapor pressure directly proportional to temperature. Keep this in mind. Okay, बाकी हम सब ये डिलीट कर देते हैं. Okay, तो, तो ओवरऑल समरी सम अप करते हैं हम. सम अप ये है, सम अप कि वेपर प्रेशर is inversely proportional to the intermolecular force and directly proportional to temperature. Okay, a vapor pressure of the solution. Second, vapor pressure of solution. Solution, here we discuss three types of solution: the liquid, 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 liquid solution. मतलब solute, liquid, solvent, liquid. Another types of solution is solid, solute plus liquid, solvent. Another type of solution, third types of solution, gas, solute plus liquid, solvent. These two types of solution we will deal from Roult's law or Dalton's law, Roult's and Dalton law, and this third type of gas in the liquid from Henry's law. We will deal from Henry's law. Okay, so write down the heading A, liquid solution, liquid solution. Let us consider the liquid 1 is component 1 and the another liquid is a solvent is component 2. Okay, suppose both these components taken in the closed vessel, taken in the closed vessel is the component 1 and component 2. This solution is a liquid phase has both the components. This is liquid phase and this is vapor phase. The liquid phase contain both the components, components A and components B. Component B I mark in the red. Sorry. Also, the component A in vapor also and component 2 in vapor phase also. The mole fraction of the component A in liquid phase, component A in liquid phase represented by the mole fraction A, and the component 2, the mole fraction of the component 2 in the liquid phase represented by the mole fraction of the component B. Similarly, the mole fraction of the component B in a vapor phase is by B and the component A in vapor phase is by A. Okay, so then the partial pressure, मतलब vapor pressure of the component in a mixture is denoted by the partial pressure of the component. Okay, मतलब ये वेपर प्रेशर ही है, मगर वेपर प्रेशर जब मिक्सचर में होता है तो हम उसको पार्शियल प्रेशर से डिनोट करते हैं. पार्शियल प्रेशर ऑफ कंपोनेंट is directly proportional to mole fraction mole fraction of component in mole fraction of the component in liquid phase. This is called this is called Roult's law. इसी को Roult's law कहा जाता है. Partial pressure of the component is directly proportional to the mole fraction of the component in liquid phase. Mathematically, Roult's law, partial pressure partial pressure of component A, Roult's law, from Roult's law, partial pressure of the component A, मतलब PA Pa is directly proportional to the mole fraction of that component, मतलब component A. Okay, a proportionality sign is equal to vapor pressure of pure component A. So Pa is equal to vapor pressure of pure component A into the mole fraction of the component A. This is the partial pressure of the component A from Raoult's law. Similarly, partial pressure of the component A, partial pressure of component B, represented by PB. PB is directly proportional to the Raoult's law. PB is directly proportional to the mole fraction of the component B, and proportionality constant is equal to the vapor pressure of pure component B. Okay, partial partial pressure of the component A or partial pressure of the component B can be calculated from a Raoult's law. Okay, here PA is the partial pressure, XA is the mole fraction of component A in liquid phase, and P naught A is vapor pressure of pure component A. Okay, similarly here XB, mole fraction of component P in liquid phase, and P naught B, vapor pressure of pure component B. Okay, now the vapor pressure vapor pressure of solution, represented by or represented by PS, or vapor pressure of total vapor pressure, or total vapor pressure total vapor pressure, represented by P total. Okay, P total. Dalton's law related to the vapor pressure of the solution of total vapor pressure. Dalton's law. Dalton's law. Dalton's law of partial pressure states that the vapor pressure of the solution or total vapor pressure is equal to partial vapor pressure of component is equal to is equal to is equal to sum is equal to sum of partial vapor pressure of component vapor pressure of the component A and component B. This means the vapor pressure of the solution or total vapor pressure is partial pressure of the component A, partial pressure of the component B. This is Dalton's law of partial pressure. The P solution or P total can be written as partial vapor pressure of component A is from Raoult's law. Vapor pressure of pure component A into mole fraction of the component A is equal to, this is from Raoult's law. This is from law. PA is equal to P naught A X A. PA is equal to P naught A X A, or PB is equal to P naught B is equal to X B. This is equation of Dalton's law. Okay. Before moving forward, we should have a look at a mole fraction. What is the mole fraction? Mole fraction is the fraction of mole. Fraction of mole. Similar, the fraction we have studied in the fifth or fourth class means, suppose a cake, if I cut a cake into the four equal parts, this is not cut in four equal part. Suppose a cake I cut into four equal part, 1, 2, 3, 4. If part 1 giving to the A, person A, and the part 2, 3 and 4 given to the person B, तो person A गिवन पर्सन ए को कितना केक दिया गया, तो पर्सन ए को कितना केक दिया, फोर में फोर टोटल, तो फोर पार्ट्स थे, फोर में से वन दिया गया तो 1/4, और पर्सन बी गिवन 3/4। ठीक है। सिमिलरली इसी तरीके से मोल फ्रैक्शन होता है। मोल फ्रैक्शन ऑफ एनी कंपोनेंट, मतलब कंपोनेंट बी, मोल फ्रैक्शन ऑफ द कंपोनेंट बी इज इक्वल टू टोटल मोल्स एंड टोटल और मोल्स ऑफ दैट कंपोनेंट, मतलब कंपोनेंट बी। ऐसे कंपोनेंट ए के जो मोल फ्रैक्शन होगा वो टोटल मोल्स अपॉन मोल फ्रैक्शन ऑफ द मोल्स ऑफ द ए, कंपोनेंट ए। ठीक है। सिमिलरली similarly similarly both similarly 1/4 or 3/4 is equal to 1. Similarly, the mole fraction of B plus mole fraction of A is equal to 1. Keep in the mind, if we know the mole fraction of the component A, we can find out the mole fraction of the component B by subtracting from 1. There we delete it. We delete it and concluded it mole fraction. Mole fraction of the component A is equal to the moles of A upon total moles. Mole fraction of component B, moles of B upon total moles, or mole fraction of component A plus mole fraction of the component B is always equal to 1. This should be kept in the mind. Okay. So from mole fraction of the component A plus mole fraction of the component B is equal to 1, the mole fraction of the component B 1 minus mole fraction of the component A. So put the value of mole fraction of component B in this equation. The P solution or total pressure is equal to P naught A X naught A plus P naught B और X B के प्लेस पर 1 माइनस एक्स ए। तो ये क्या होगा, P नॉट A एक्स ए प्लस P नॉट B माइनस P नॉट B एक्स ए। rearrange these terms. सेम मोल फ्रैक्शन को एक साथ ले लेते हैं और बी पी नॉट बी प्लस पी नॉट ए एक्स ए माइनस पी नॉट बी एक्स ए इफ पी नॉट बी और एक्स ए को कॉमन लेंगे तो पी नॉट ए माइनस पी नॉट बी. This is another equation for Dalton's law. Okay, this is another equation for Dalton's law. A partial pressure of the component A from Dalton's law, partial pressure of component A from Dalton's law. The partial pressure of the component A is directly proportional to the mole fraction of A in vapor phase, where in Rault's law, the partial pressure of the component A is directly proportional to the mole fraction of the component A in liquid phase. So in Dalton's law में partial pressure of the component A is directly proportional to mole fraction of the component A in vapor phase, or proportionality constant is equal to P total pressure is into mole fraction of the component A. This is the partial pressure of the component A from Dalton's law. Similarly, the partial pressure of component B from Dalton's law. Partial pressure of the component B is directly proportional to the mole fraction of the component B in vapor phase. मतलब partial pressure of the component B proportionality constant is equal to P total. तो proportionality को रिमूव करने पर हम P total यहाँ पर रख देंगे. ठीक है, P total is equal to partial pressure of the component B is equal to P total into mole fraction of the component B in vapor phase. तो टर्मिनोलॉजी यहाँ याद रखना बहुत ज़रूरी है कि यहाँ पी ए पार्शियल प्रेशर है, पार्शियल प्रेशर ऑफ ए, और पी टी टोटल प्रेशर है या प्रेशर ऑफ सॉल्यूशन है. बाई ए इज द मोल फ्रैक्शन ऑफ ए इन वेपर फेज. किसमें में? वेपर फेज. ठीक है. सिमिलरली पी बी पार्शियल प्रेशर ऑफ बी, पी टोटल प्रेशर और प्रेशर ऑफ सॉल्यूशन, और बाई बी इज मोल फ्रैक्शन of B in paper phase. Till now we have two laws or two formulas to find out the partial vapor pressure of the component. First from Rault's law and second from Dalton's law. The partial pressure of the component A is equal to partial pressure of the component is equal to partial vapor pressure of the pure component A and the mole fraction of that component in liquid phase, or or the partial pressure of the component A is equal to P total, the vapor pressure of the solution, or total vapor pressure or mole fraction of the component A in vapor phase. This is from Raoult's law. This is from Dalton's law. Both have a same value. So whatever given in question, if the mole fraction given in paper phase, we can find the partial pressure of the component A from Dalton's law is equal to Pt by A. If the mole fraction of the component A given in solution or liquid phase, then we can find the partial vapor pressure of the liquid A from the Raoult's law, that is equal to P naught A into XA. Okay, both will give the same value, but the difference is only the what data given in question, if data given in question about the vapor pressure and mole fraction in vapor phase, or vapor or mole fraction in liquid phase. Okay, both give the same value. Second types of solution, second types of solution is the solid liquid solution. Solid liquid solution, where the solid where the solid is non-volatile solute, non-volatile solute, and liquid is volatile solvent. Okay, then from Dalton's law, vapor pressure of solution, the P total is equal to partial pressure of the component A plus partial pressure of the component B. Here the solute is the component B and solvent is the component A. So solute is non-volatile, that is component B is non-volatile. This will produce a no vapor and form a no and constitute no vapor pressure. This here is vapor pressure 0. The vapor pressure of the solution means P total. P total is equal to vapor pressure of solvent. A vapor pressure of the solvent can be written from Roult's law. Partial vapor pressure of the solvent in solution, vapor pressure of pure solvent A, and mole fraction of solvent A in the liquid phase. This is called vapor pressure of a solution containing a non-volatile liquid. Vapor pressure of solution containing non-volatile liquid. Okay, why this happen? Let's see. Suppose a container. Suppose container. Suppose a container having a pure solvent, pure solvent, pure solvent. Okay, the vapor pressure of the pure solvent is P naught, which is equal to 5 atm. Suppose 5 atm. If we add non-volatile solute in it, pure solvent is non-volatile solute in it. We, up here, the surface occupied a non-volatile solute also, like this. Earlier in the pure solvent, the whole surface is occupied by the solvent, volatile solvent. So here the vapor pressure of the pure solvent is always higher than the the vapor pressure of solution, non-volatile solute, solution containing a non-volatile solute. Here the fraction of the surface containing a volatile solute is reduced. The fraction of the surface containing a volatile surface is reduced, whereas mm, whereas whereas the whereas vaporization or evaporation, the surface phenomena, to, to escaping tendency of the solvent molecule is reduced, then the vapor pressure is reduced. The vapor pressure of the solution is reduced. Vapor pressure of solution, P solution, is equal to 4. Pure solvent is 5 and solution is 4 atm. There is a reduction in the vapor pressure of the solution due to occupancy of the non-volatile solute at the surface of the at the surface of the solution, where the less solvent molecules occupied at the surface of the liquid. Therefore, the tendency of the solvent molecule to escape is reduced, hence the vapor forms is reduced, hence the vapor pressure is reduced. Okay, so noted down one important point: the vapor vapor pressure of the solution is is always less than pure solvent. Okay, now we will discuss about the graph of the liquid solution and the solid and liquid solution. Graph vapor pressure versus mole fraction कैसा होगा? लीनियर और स्ट्रेट लाइन. Okay, graph drawn in such a fashion where the y-axis have a vapor pressure and the x-axis has mole fraction. Suppose here the mole fraction of the component A is equal to 1. Component A is equal to 1 and the component B is equal to 0. As we know, the mole fraction of the component A plus the mole fraction of the component B is equal to 0, is equal to 1. So what this implies, that component A is equal to 1 means the component B is 0. Okay, or a component in this side component A is equal to 0 means the component B is equal to 1. Component A is equal to 0, then component B is equal to 1. Both component mole fraction of the component A is equal to plus mole fraction of the component B is equal to 1. Here is the component A only. Well, this is the pure component A. The pure component A vapor pressure is represented by P naught A. P naught A. Here here the mole fraction of the component A is 0. Mole fraction of the component B is 1. Matlab here is the pure component B whose vapor pressure P naught B by the vapor pressure of the pure component A is on lower side than the vapor pressure of the pure component B. This is because the component A is more volatile than component B. Then vapor pressure of the component B is greater than component A. Component A is more volatile. No, sorry. Component B is more volatile than component A. Then component vapor pressure of the pure component B is greater than the vapor pressure of the pure component A. Here the component A, mole fraction of the component A is highest as we move towards the right. As we move towards the right, the mole fraction of the component A decreases as we move left. Mole fraction of the component B decreases. From Rault's law, we know that the vapor pressure, partial vapor pressure, is directly proportional to the mole fraction of the component. Okay, then mole fraction of the component here is the highest vapor pressure. A mole fraction of the component A decreases from left to right, means vapor pressure decreases from left to right like this. Here the vapor pressure of the component B is highest here. Okay, as we move from right to left, the mole fraction of the component B decreases, means vapor pressure of the component B decreases like this and become 0. This line represents partial pressure of the component A, or this line represents the partial pressure of the component B, and joining the vapor pressure of the component pure component A and the vapor pressure of the pure component B, this line represents the vapor pressure of the total vapor pressure or a vapor pressure of solution. Okay, okay, this is the graph when component A and B are volatile, but B is more volatile than A. Okay, liquid solution. For a liquid solution, graph for solid liquid solution. For solid liquid solution, P total is equal to partial pressure of the component A, that is vapor pressure of pure component A and mole fraction of the component A. From this equation we can draw the graph like this: P total and mole fraction of the solvent, mole fraction of the solvent like this, and the slope is equal P naught A, vapor pressure of the pure component A.